Okay, today I'm going to show you how to assemble one of these inverter logic kits, and we will start with what you get, this box of parts. So when you open it, you will see a list that contains all parts that are in this box, and they all have an ID number. So when you grab one of those bill of materials that you can print out from the website, you will find, I don't know, R14 10K, and then you go to this list, 10K, which is ID number 19, and then you start searching for number 19, which would be this one. It says 19 right here. Some parts a little plastic bag and ID numbers in there, or some very obvious parts that are only used once don't have ID numbers, they just only fit in one place. Yes, so that's how this ID system works. So I just start unpacking all the parts. The new kits come with a new serial cable. I put a note on it: never connect the red wire. The red wire is 5 volts, and if you connect it to the 3.3 volt input of the board that you'll see later on, you might be destroying some stuff. So don't connect it. Okay, so now everything is spread out. While doing that, you can also count if all the components have been shipped. And now you're good to go to do the actual population of those boards. So I'll introduce them to you real quick. This is the most important board. It's the inverter main board, and it carries all the logic that is needed to measure some of the inputs, like the pot, and to generate the PWM outputs to drive the power stage. So that's that. Then you've got a sensor board. So this basically delivers 4 signals to the main board. It's 2 currents, 1 bus voltage, and 1 heatsink temperature. And lastly, you get 3 copies of this gate driver board. That's 2.5 amp gate driver that works with IGBTs up to 400 amps. That's at least what I'm using. People have used it with 600 amps, works as well. So that's your call really, if this is sufficient. Okay, so populating parts. Yeah, I'll just give you an example how to do this. I won't actually be soldering because I'll be messing up this PCB, but I guess you get the soldering part yourself. I'll just get one of those caps to give you the idea. So on the bill of materials, we're looking at the very first part, and that is C1, 22 nanofarads. So I go to this list, 22, it's ID number 1, so it's the part in this bag. So I got a copy of the part here. So you go and find the label C1, that's right here, and you turn the board over and bend those pins outboard a little bit so it doesn't fall out. Then get your soldering iron, get your solder and solder it in place, cut off the excess leads, and you're done. So when you're done populating the main board, that's what it will look like. All nicely soldered in place. This is the back. And you can do a first power up test now. before you actually put on the Olimax board, because you want the voltage to be at the right level to not damage everything. So that's what we're going to do. I've prepared a ribbon cable. This lock goes in place and there's no way this can ever fall out. Okay, just going to make some space, and I've prepared this. Just connect it to another power supply. Okay, so now as you can see, I've set this to 10 volts and 170 milliamps. So it's a really low current limit. In case there's any short in here, we will reach this current limit and don't damage anything. So let's switch it on. And we see there's hardly any current. We're just supplying those few ICs and that's it. So let's get out a meter. Let's see what the voltages are like. Put some nuts in here. So this regulator is a good source of ground, and we are expecting, well actually no, the input voltage goes to pin, to this very outermost left pin, so that should read the same as here. And just gotta arrange this in a way so you can actually see it. Around here. So that reads 10 volts. And the output, we can see that on the cap right here, for example. That should be 5 volts and it's 5.03 volts. So that's good. Okay, now first thing we'll do is test the communication. Just black cable is ground and it plugs into JP6 to the pin right next to this little inductor right here. Then comes the green cable, and then comes the white cable. Okay, power up. You can see the red LED indicates power, green LED flashing indicates the running software. Okay, so now we connect to this, plug it in. Hope you can see anything here. There's a couple of ways to connect to this. I prefer the web interface. So you install that on your computer, there's instructions for that, I'm not going to repeat this now. And it comes up like that. Sometimes you get some errors, just press F5, load it again, and that will fix it. So, let's start from top to bottom. Got some buttons up here. First one, once you've done some configuration, you can save your parameter set to the flash on this Olimax board, so then every time it starts up it will load your configuration and use it. If you've configured stuff and feel you've messed it up, you can restore the parameters from flash. You can also restore them by just toggling the power. That will also load them from flash. Start inverter in manual mode, that's for testing. That will switch on the inverter without you having to play with the input pins, and stop inverter stops it. There's a link to the parameter reference, goes to my webpage to a site that has some words on the parameters. Then here's a button that allows you to download your current parameter set to a JSON file, and in the other direction you can upload the configuration. Okay, so if you want to change the value of the parameter, just type in the new value, 2000, press enter, and you can see here it sends a command to the inverter board, and it replies set OK. If I were to type in like some access value, it will tell us, oh, that didn't work, value out of range. And yeah, if you update the table, you can see it jump back to its previous value. Okay, then spot values is some measurements. Might be interesting. You can plot, like if you do a test and you want to record the speed, you say you want this on the left y-axis, and you start the plot, and then it will pull 10 values per second and plot them right here. Not much happening right now as there's no speed. Okay, so we've established communication is working. One other way to talk to this inverter, if you for some reason don't want to use the web interface or can't use it, there's a regular serial port terminal. This one is a Linux version. Windows hyperterminal will work just as well. And you can type commands like list, and it will give you a list of, well, basically that list. And you can say set boost 5000, and that will do just the same, sets it to 5000. Same way you can say get current 1, comma current 2, and that will get you these values. So this is pretty straightforward, just some more typing work. And you can't use both at the same time. You can use the terminal while this web interface is being displayed because it doesn't actively do anything. But once you start using the web interface, you have to close the terminal, otherwise this will request values and the terminal receives them, and this receives nothing and it won't work. Okay, communication working. Time for the next step. Okay, so now we want to see if we can get some pulses out of this thing. So there's a couple of prerequisites that need to be met to make it run, because there's some hardware logic that shuts off the PWM as soon as stuff isn't as expected. One part is the current sensors. If their value goes out of range, the PWM is shut down by hardware. And then there's two signals on this wire harness right here that also shut off the PWM if they are on a low level. So they need to be tied high for the PWM to work. It's a bit hard to get the numbers of these, because I've kind of mirrored and twisted this thing a couple of times, and then someone found out that the pin numbers don't really match with the cable number right here. So this isn't pin 1, this is pin 2, and then 1, and then 4, 3, and 6, 5. I've put it up on the website, you can see it there. Okay, so there you have it. There's 4 cables tied to my plus voltage and 1 cable tied to my minus voltage. 4th cable is the power supply. Good. I've turned on power. So now we can see if this is going to run. So we start inverter in manual mode. It says right here, inverter started. Then you go right here. and you see F slip set point is at -1, which basically shuts off the PWM. We set it to 1, and then amp non also has to be greater 0, because otherwise the PWM isn't running. Okay, so now you can see on the scope we have a nice clean 50-50 duty cycle. And if we now increase the amplitude to like 100%, you see this is like getting wider and smaller at the 1 Hz frequency that we set. And the amplitude rises with frequency. This is VF algorithm, if you want to call it an algorithm. So if I set it to 10 Hz, not only will it swing faster, it will only swing more. There you see it. So this is looking good. You get this kind of signal on 6 pins here. This is set up. Pin 1 is always 5 volts for power supply of a gate driver. Then pin 2 and 3 is the top and bottom PWM signals. And you get another 5 volts. And then the PWM signal of phase 2, top, bottom, 5 volts, PWM. Oh, and the last one is ground. So displays nothing. Okay, so we have 6 PWM signals that are modulated as a sine. So we're good to move on to some more power. Okay, so we jumped ahead quite a bit. Here you can see all the viable components of an inverter. We've got this well-known processor board here. We've got the current sensor board here. And we have the gate drivers, 3 of them here. Now there's some important points. You can see that the connections from the gate driver boards to the IGBT is twisted. And that's so that spikes don't inductively couple into only one of those, but into both, and then differentially it won't make any difference. You can also see on the power stage itself those large bus caps, and those catch the spikes that turn up when the IGBT switches off this inductive motor load. And the caps have to be really close to the IGBT, because every centimeter or every loop area in the DC bus path means higher voltage spikes. So this one isn't perfect, but it's pretty close. There's no long cables between the IGBT module and the caps. There's 2 in parallel. Those are a bit oversized. They're 420 microfarads and probably take up about 100 amps of ripple current each. So 200 amps ripple current capability, but the power state is only 80 amps. So rule of thumb is you take the motor RMS current and divide it by 2, and that's what your ripple current rating of the caps should be. So 40 amps ripple current rating would be enough, so a much smaller cap would do the job. Okay, now we will do some testing on the gate driver boards. Be right back. Okay, so now I've connected a probe to each of one of the gate driver outputs, one high side, one low side, and the DC bus is not connected to anything, so they're the same potential, and you can see 5 volts per division, and we are 3 divisions down, so about minus 50 volts. Now if we start, you can see now one is switched off. It's A probe, that's the high side is switched off, the low side is on, plus 15 volts. Next thing is we will, as before, set the frequency set point to 1, set the amplification to 1, and here we get duty cycle. Now it is important to see that there's some space left between this one going down and this one going up. There's a parameter for that, it's called dead time, and it's set to 63 right now, which means I think 1.5 microseconds. Yes, so that's all we need to see right here. You'd have to check this on all 3 gate drivers. It should always look exactly the same. And now we're ready for some more power. Okay, so now I have connected my lab power supply to the DC bus, and it's limited to 10 amps, so even if things were going wrong, the current would be limited, nothing would happen. You can see it reading some current, and that's because I've connected this motor brake. This motor has a brake in the back, and you have to put a certain current through it so it releases. So this is basically our 0 point right now, just the brake. If I remove it, it's gone, no more current. And that's what we want, no shoot through, nothing happening. And now we can start to give the motor some current. Okay, so now we are running at 2 Hertz and an AC voltage of about 2 volt. Now this is a low voltage forklift motor, and let's see if it's in the camera, you might be able to see it spinning. Here you see it. Okay, so this is all working, and we can go to even more power. So, the inverter is now connected to my 2 lead acid batteries, 24 volts, that match the motor voltage pretty well. Batteries are fused, of course. That would be a large bang if some short were to happen. And we've connected the probe to the DC bus. And we can see on the scope it's no longer very DC, but it has some of the switching frequency spikes still on, and these spikes would be much larger if there weren't any caps, or too small, or with a too large inductance. Okay, so now that we have the batteries, we can spin up this motor. So I've set up the inverter with the parameters that matches this motor. You'll find the formulas for that on the website. And now we can manually control the speed. This is still the volts hertz mode, which isn't particularly useful, but it's good for testing. So let's go to 10 hertz. That didn't really do much. Again. Oh, there we go. 20 hertz. 30 hertz. Okay, that was a bit too quick. Seems we surpassed an overcurrent limit again. Okay, so what we really want to do is torque mode. And for torque mode, the controller needs to know the current rotor speed, and this motor has a speed sensor built in we are going to use. Now let's do that. So we now have the encoder connected. It's not even shielded cable, but first test run it even worked. The power supply is just keeping the batteries on a good charge. Not doing really much. Okay, and the inverter is once again started in manual mode. And the maximum frequency is set to 100 Hz, so it doesn't blow off the table. And we can start by setting a slip frequency of 2 Hz. And we will do some recording of currents and frequency. Doing that. Let's go. Okay, so now it's spinning at 100 Hz. It's wobbling a bit because the inverter constantly cuts back power to keep it below 100 Hz. Now if I enter a negative slip frequency, minus 2 Hz, we get a massive regen and the motor will come to a standstill. That's how quickly it stands still. Well, this is torque mode. No more speed control. And because the motor isn't loaded, there isn't really any means of doing speed control. Because very little torque will just put it to its maximum frequency. Just for the fun of it, we can spin a little higher, like 200 Hz. See what it does. Let's go. It's like the same story, just quicker. So there we have it. Torque control of an induction motor using just speed feedback. Done for today.